So let's continue talking about this trig stuff here. In an ideal scenario, you would know these trig values super well, and you wouldn't have to reproduce the unit circle every time. In fact, once you really understand the first quadrant super well, you can always just use symmetry to figure out the other quadrants, right? So in the past, I've taught students a method of how to really find all the trig values in quadrant 1 really quickly. So maybe I should mention as well that these quadrants have names. So this first quadrant here, this is quadrant 1. The second quadrant is on this side, that's quadrant 2. The third quadrant is here, this is quadrant 3. And the fourth quadrant is on this side, quadrant 4. So when I'm talking about quadrant 1, I'm really talking about positive x and y values. Okay. And there's a really fast way that you can fill out this table so that you can get all the trig values. And it's pretty cool. So I just want to show you. The first thing I want you to notice is that when we're in this first quadrant, we can really write these so that all these points have a denominator of 2. So earlier I discussed how we could rewrite this as rad 2 over 2 and rad 2 over 2 like this. And for the purposes of filling out this chart, that's going to be useful for us. Okay. So watch what I do here. What I'm going to do is I'm going to put a denominator of 2 all the way across. Okay. And then what I'm going to do is the numerators all have these very special numbers. And all I'm going to do is write the numbers from low to high. So like the first special number we have is like 0, right? So I put a 0 here. Then the next biggest number I have is 1. So I put a 1 here. Then the next biggest number I have is rad 2. So I put a rad 2 here. Then the next biggest one is rad 3. And I put a rad 3 here. And the next biggest number I have is 2. And I put a 2 here. So all of my fractions involve these numbers. So I just write them in ascending order from low to high. And if you look, if you check, these are exactly the trig values for sine. So that's kind of cool. The next question you say, well, what about cosine? So I do the same thing. I divide everything by 2. But before I went from low to high for sine, and for cosine, I'm going to go from high to low. So I go in the reverse order. So this becomes 2. This becomes rad 3. This becomes rad 2. This becomes 1. And this becomes 0. Right? So I didn't even need to really think. All I got to do is just write everything from low to high and from high to low. Now for tangent, we are going to use that quotient identity. So it's important. So I'm going to remind you again. Sine theta divided by cosine theta. But the way I wrote my chart, I have sine theta automatically on top of cosine theta. So I'm just going to divide those two numbers. So 0 divided by 1 is 0. 1/2 divided by rad 3 over 2 is 1 over rad 3. In case that's not obvious, I can write like this: 1/2 divided by rad 3 over 2. As I explained to you earlier, dividing by a fraction is the same thing as multiplying by the reciprocal. So it looks like I maybe want to flip the bottom fraction. So this becomes 1/2 times 2 over rad 3 like this. And then these 2 cancels out, and then you get 1 over rad 3. So that's how I got that, just in case it wasn't obvious. Okay. We divide the next two, it's the same number divided by itself, so that's going to be a 1. We divide these two guys, that's going to be a rad 3. And then anything divided by 0 is undefined, so this is undefined. Is there any questions about this? So in the past, I've taught people this chart, and then before a calculus exam, there's a technique called dumping, where you've memorized all this stuff that you don't want to forget, and then you sit down when it's time to take your test, and you just dump all the information on a piece of scratch paper. So sometimes students use this table to do that. Okay. All right. I don't consider trig identities to be a separate approach because it's kind of universal to all the approaches in a way, but trig identities are kind of important. So let's continue with these trig identities. The reciprocal of tangent of theta is actually 1 over cotangent theta. So I feel like that should be a 3 maybe. I feel like 3 and 4 are kind of saying the same thing. Okay. So the Pythagorean identities, I don't know if you remember, but earlier we were talking about the Pythagorean theorem, right? You had the A, or maybe you had like A, B, and C like this. And then you got that C squared is equal to A squared plus B squared. So there's this famous story about Pythagoras. He was this religious fanatic that they really worshiped like rational numbers. So they thought everything in the world could be expressed with a rational number. What's a rational number? It's just a number like 7 over 3. You know, it's just a quotient of 2 integers. And the ultimate irony is he creates this theorem that gives you the third side of a triangle. So it's kind of like, because of his theorem, when you look at the triangle 1 to 1, what's that third side going to be? That's going to be rad 2. And rad 2 is not a rational number. You can't write that as the quotient of 2 integers. So here he is. He's the head of this religious sect. They worship the rational numbers. And his theorem creates a number that ruins his religion. So it's kind of messed up. But life is interesting for sure. So that's a totally unnecessary story. But it turns out that there's trig identities that look like these this Pythagorean theorem. So by far the most famous is sine squared theta plus cosine squared theta is equal to 1. Okay. And then what you can do is you can pretend in your mind, I'll write it down, but pretend in your mind that you divide through by sine squared theta. When you do that, what's your result going to be? Well, sine squared theta divided by sine squared theta is 1. Cosine squared theta divided by sine squared theta is cotangent squared theta. And 1 over sine squared theta is cosecant squared theta. Okay. So we used the couple of quotient identities. We used a quotient identity and a reciprocal identity to get the next 2 terms there. Instead of dividing by sine, what we could have done is we could have divided by cosine. So if instead I divided by cosine squared theta, then what would we get? Well, that first term now becomes tangent squared theta. The second term becomes plus 1, and the last term becomes secant squared theta. Okay, so these 3 trig identities, these 3 trig identities are kind of essential for life. We use these a lot in 5B. So if we take 5B together next semester, I'm going to review this with you again. Any questions? All right. Let me see here. So we have addition and subtraction formulas. Sine of x plus y and cosine of x plus y. I think these showed up in your error analysis group work that some of you did. Hopefully you took the quiz. You can take it multiple times and just brush up on your intuition. Students dream that it's sine of x plus sine of y, but that's totally false. It's not true at all. Sometimes an easy way to remember something is to make it so ridiculous that it becomes simple. Like, ridiculous things sort of stick out in your head. So I have difficulty remembering people's names. So sometimes I try to use their name and remember it in this really weird, outlandish way. A student helped me remember these formulas. And she taught a song to me. I mean, it's not really a song. It's more like a ditty, like a jingle. Anyways, here's how it goes. You ready? It's kind of lame, but the lameness helps you remember it. She goes, sine, cosine, cosine, sine, cosine, cosine, sine, sine. Now, it sounds ridiculous, but I could never remember these before the student taught it to me. So sine, cosine, cosine, sine, cosine, cosine, sine, sine. Right? Now you still got to fill in the angles, right? So you still got to put in the x and the y and the x and the y and the x and the y and the x and the y. Okay. And the sine has a plus in between and the cosine has a minus in between. So this is the addition and subtraction, addition formulas for trig. So there's something called double angle formulas. So you got sine of 2 theta is equal to 2 sine theta cosine theta. And you could see that just by putting a theta in over here. If you put a theta here and a theta here, you put a theta here over theta, theta, and theta like that. Can you see that you're going to get 2 sine theta cosine theta terms? When you add them together, you got 2 of them. So that's how you can see that. Okay. If you looked at cosine of 2 theta, how would we figure out what cosine of 2 theta is? Well, I could just come over here. I could just put a theta here and a theta here. That gives me a theta here and a theta here, a theta here and a theta here. So when you do that, you can see, oh, I'm going to have cosine of theta twice, cosine of theta squared. So this is cosine squared theta minus, I have sine theta multiplied by itself. So it's sine squared theta. In actual fact, there's 3 versions of this. The 3 versions, you can also, you could use this first Pythagorean identity and then sort of join it with filling in these 2 parts over here. So let me give you the other 2 versions. Let's just leave it, actually. You really need it for 5B. You don't need it so much for this class. Okay. Great.